Let's imagine a reaction between a molecule A and a molecule B that occurs when A and B collide and form products. In order for this reaction to happen, A and B have to collide, and then that collision has to have enough energy for those two molecules to rearrange and to form products. And so we could imagine that the rate of the reaction would depend on how fast the collisions occurred, so the rate of collisions, but not every collision is going to lead to reaction, and so that rate of collisions is going to have to be multiplied by the fraction of those collisions that have enough energy to react, because only the fraction of collisions that have enough energy to react are going to actually form products. And so if we multiply by that fraction, we should get the number of collisions, or the fraction of the collisions that actually have enough energy. And then if this is the rate of collisions, the fraction that have enough should give us the rate of the reaction. There's one other factor that's important here, and that is the orientation of the reactants. If we take as an example this reaction between hydroxide and methyl chloride, we can see that to make the products, we have to form a carbon-oxygen bond and break a carbon-chlorine bond. And to make that carbon-oxygen bond, it's only going to happen if the oxygen bumps into the carbon from this end where it has a place where it can make a bond. If it bumps in from the side with the chlorine, there's no way for it to access the carbon and to make a bond to the carbon. And so the direction or the orientation of this collision is going to make a difference. So if we look at this reaction, we can see that the oxygen has to come in and make a bond to the carbon, and the chlorine has to leave. And that will only occur when we have the right orientation of the reactants. And so we're also going to have to multiply by the fraction of collisions that have the right orientation to react. Our collision rate is given by the cross-sectional area of the collision between A and B times the relative velocity of A and B times Avogadro's number times the concentration of A times the concentration of B. And our fraction with enough energy to react comes from the Maxwell-Boltzmann distribution and is the exponential of minus activation energy divided by RT. The fraction with the correct orientation is just going to be designated by the letter P, and that will designate the fraction that has the right orientation to react. And so when we multiply all of these things together, we should expect to get the reaction rate. So you'll notice, let's put this all together, that the rate is equal to a bunch of variables that have to do with the molecules themselves, cross-sectional area of that collision, the relative velocities of the molecules, Avogadro's number, and the orientation, the fraction of molecules that have the right orientation to react. And then we have a factor that depends on the activation energy, how much energy is required to react, and the temperature. And so we have e to the minus e sub a over RT. And then we have the product of the concentrations of the two species, the two molecules that are colliding with one another. And so we expect our reaction rate for a collision, for an elementary reaction that occurs between two molecules, to have a whole bunch of things here times the product of the two concentrations of the two species that are reacting. This stuff that precedes this power law in the concentrations is what we call the rate coefficient for the reaction. And so we often give that the symbol K and just write this as K times the concentrations of the things that are colliding. This rate coefficient, notice, depends on the temperature, because the higher the temperature, the faster the molecules are going, the more collision energy they will have, and the more likely they will be to overcome the activation barrier. And so as I increase the temperature, I increase this rate constant, and thus I increase the rate of the reaction. It also depends on the size of the molecules that are reacting, because the bigger they are, the more likely they are to collide with one another. And so the larger this cross-section is, the faster the rate of the reaction. And then, of course, it depends on the orientation, and so I have to multiply by this orientation factor P that tells me what fraction of the molecules have the right orientation to undergo that reaction.